This is part 6 in this series devoted to Improv Card Magic. Now today we will be looking at 16 card packets, 16 cards. And so to begin this, what we will need is 3 random piles of 16 cards each. Now this is going to use up most of the deck, as you might imagine. So I'll go ahead and just deal them out, 3 piles of 16 each. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Whoa, look at that. Just 4 cards left over, which is what we would expect. Okay, so we have these 3 piles of 16 cards each. Now, I do want to review something that we talked about in the previous video in which we looked at 14 card packets. And so this is a little system that I came up with to essentially make remembering color pairs easier, okay? So for example, let's say we lay out the cards, and from the top of the deck we have a red, 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 black, 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 and so forth, all the way to the bottom card, which happens to be black, okay? Now if you remember my system, what you can do to quickly remember how many red pairs you have and how many black pairs you have, and we're going to ignore the color pairs that don't match. So for example, right here we see 2 red cards together. Okay, so if we view this as an AMP, these 2 cards would be, quote, related. So what we can do is we will count a red pair as 10 and a black pair as a 1. So that when we add all of these values, the tens place will simply tell us how many red pairs we have, and the ones place will tell us how many black pairs we have. So for example, we have a red pair here, so in your mind think 10, nothing here, and we have a black pair, so that counts as a 1. So 10 plus 1 is 11. Another black pair, so plus 1 is 12. So just keep a running count. Plus 10 more for a red pair. So now we have 22 as our number. Nothing, nothing, plus 1 more, 23. So the only number, or the only information we would need to remember until the end of the performance is the number 23. And then when we go to use that number, we'll look at the tens place, which is a 2, and that will tell us that there's 2 red pairs, and the ones place, which is a 3, and that would tell us that there are 3 black pairs. Okay, so we'll kind of use this little system for remembering how many color pairs we have. Okay, so let's go ahead and just move these up. I guess we can just begin with the one on the left here first. And then recall, we're going to have each pile associated with a packet structure. So for the first one, we're free to go with either one of the packet structures. It'll probably just depend on how strong, how surprising it will be to go with a certain packet structure. Okay, so let me try that again here. These are brand new cards, brand new cards here. So I'll see if I can kind of fan them out so that we can see what's going on a little bit better. Okay, that's mildly better, I think. Okay, so if we want to view this as an AMP, which we could, so here we have opposite colors, so you can think of that as a 0, so we don't add anything. A pair of red cards, so that's like a 10, nothing, another 10, so we're up to 20, a black pair, now that's 21, nothing, nothing, nothing. So associated with the AMP structure, we could just squirrel away the number 21, and that will tell us how many red and black pairs we'll have at the end. Well, I mean, we don't have to go with color either. Now that's the key. We can look at any characteristic of interest Oh, wow. View it now as an AMP. I'm not going to rearrange anything. So look at these two. Okay, opposite color, fine. But check out these. 2 red, 2 aces, 2 sevens, 2 threes. Oh, too bad we don't have 2 fours there. Okay, those. Oh, wow, we do. We have 2 fours here. 2 and 8. Wow, so we could go with, it might be fairly strong, we could say we have a 1 pair matching in value, so we're not worried about color anymore necessarily, right? So we have a pair of aces, so 1 matching in value, a second one, a third one, a fourth one. That's interesting. So 4 of these pairs match in value. I don't know. I think that might be fun to go with. So, and you have to realize that for us to know anything about the ending packet after all of the mixing we're going to do, it will be a miracle if we know anything at all. So I'll just write down here. So 4, and we'll say matching card. This is probably writing down more than we need to. I'm being verbose here. 4 matching card value pairs. As long as we can decipher what that means. And so that means there's 4 pairs where within each pair the cards are of the same value. Okay? So if in your mind, I don't know if a person could probably remember that without having to write it down. You just have to realize that for the sake of this video, we're going to do 3 independent routines. Now, normally you would just do 1 of these. Well, because we're doing 3 of them, it's probably unrealistic for us to remember all of these and keep them straight. So that's why I'm jotting down some notes. But if this is the only thing you're going to do, you would just have to remember the number 4. And remember that it's associated with 4 pairs of cards that have the same value within the pair. Okay, that's not too hard to do. And a way to remember the number 4 is perhaps to just remember that there's 4 suits, okay? Or any way to remember that 4. Maybe there's 4 people in your family or 4 siblings or whatever significance 4 might have for you that would help you remember it by way of a mnemonic or something, okay? Think of the 4 seasons. I just thought of that one as well. Except for where I live, there's only 2 seasons. So just remember the number 4, viewing this as an AMP, and then this one over here was for the AMP, okay? And maybe just to remind yourself, what is it about the AMP? Do you remember? We needed to remember the number 4, like 4 seasons. What was it about 4? It's because 4 of the pairs are of the same value within each pair. You remember that? So 4 matching value pairs, okay? So that's all you need to kind of remember for this packet. Now, since it is an AMP, there's quite a few things you can do with it and preserve that structure or convert it to another kind of structure. So let me go ahead and just bring up our basic shuffles that we've been using during this entire series. Okay, so as an AMP, if you go down to line 21 on the left-hand side of the screen, you'll see the AK, alternate Klondike shuffle. And this is guaranteed to convert an AMP to a 2-cycle, okay? So how this works then is you just deal them out, left, right, left, right. Now I do want to point out that you could actually do what we're doing here, but do it into 4 piles or 8 piles. You can deal out these pairs into as many piles as the divisors of the packet size. Of course, the packet size is 16, and the divisors are 2, 4, and 8. Well, I just did the standard alternate Klondike, left, right, which is fine. But this plus J refers to Klondike shuffling pairs into 4 piles and so forth. And then we can stack those in kind of different ways than just left to right or right to left. So this judicious stacking is something I talk about extensively in other videos on this channel, so that's something to watch for. But here I just did a left, right, okay? Now this is random stacking decided by the spectator. Maybe they want right on left, that's just fine. Now, since it's a 2-cycle, we can perform as many cuts, so random cut like that, or more impressive, we can do a Charlier shuffle, top to bottom, bottom to top, top to bottom. Okay, and I have, as I've mentioned, a separate video on the Charlier shuffle. So all of that movement of the cards is equivalent to just cutting the cards at some location. Well, because packet cuts do not hurt cyclic constructions, and in particular a 2-cycle, this is still a 2-cycle. Okay, now what we're going to do is we're going to do an LR inverse. You can also think of that as an LR quote 8, okay? And so what we're going to do is I'm going to just deal out into 8 piles. Now I won't be able to fit 8 piles here, so we'll probably just do 4 and then 4, okay? But just realize that you can, if you had more space that you can use than the camera view here, you can deal out into 8 piles from left to right. That would be fine. And it might cause fewer problems keeping things straight, okay? Now, technically, this is a DMP now, right? So think about it. If it was a 2-cycle, that's like having 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Well, by the time we deal out 1 through 8, and then we deal out 1 through 8 again, we've grouped together all the quote 1s, the 2s, the 3s, and 4s, and so forth. So this is what we've been calling a DMP. It's right down there, a DMP. So you can freely stack these however you like, or however the spectator would like. So maybe they want this one picked up first, and then maybe this one, that's fine. This one way over here, that would be great. This one down here would be fine. This one down here would be great. This one over here next, that's fine. This one over here would be fine, and then this one next, okay? So what that gives us is it gives us an AMP again, okay? Which is amazing, an AMP again. Okay, now what we're going to do is a push-off even numbers of cards, and this is found on line 19 in the chart on the left. Now, since this is an AMP, it means everything of importance happens in pairs. So if I push off any even number, maybe I'll push off 2 there, and then 4 here, and then maybe 2 there, and then maybe even 6 over here, and then 2 here. Okay, we are free to stack these however we would like, or however the spectator dictates. Okay, so maybe they want this one picked up first, that's fine, maybe this one here. So just think about all the free choices we're giving the spectator, because surely these choices make a difference to the ordering of the cards, which they do. Okay, but this particular procedure that we've just used will not harm AMP structures. That's the key. That procedure would destroy mirrored structures and 2-cycles utterly, but not AMP structures. Okay. Now we're going to convert it to a mirrored structure now by way of the mange. And so if you take a look at the table on the left, it's line 13. And that will always convert an AMP to a mirrored structure. And if you remember, the mange shuffle comes in 2 varieties, an over-under and an under-over. And you can give the spectator that choice. So maybe they'll go with the over-under, 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 over. Okay? We are guaranteed to now have a mirrored packet. And once it's mirrored, you can do LR shuffles. Now here, because of 16's divisors, we could left-right deal into 2 piles, 4 piles, or 8 piles with random stacking from left to right. And that's because of the stay stack principle. Okay. Now what we're going to do a little different though is we're going to go ahead and just deal out half the cards and then flip either half. That's interesting. Okay. So think about what this will do. If I deal out half the cards, 1, 2, 3, 4, 5, 6, 7, 8. And so that's called a 50% coding. If I were to follow it up with the rest of the cards being dropped on top, that is, quote, a 50% coding of the cards. Well, if you take a look at our chart on the left, a 50% coding on line 5 will convert a mirrored structure to a 2-cycle structure. Okay, that's guaranteed. That means setting them side by side like this, they constitute coupled piles. What are coupled piles? This is where at each level the piles are related in the way that we noted at the beginning. Well, guess what we're going to do? What we're going to do, instead of just stacking these, because we would get a 2-cycle then, we're going to randomly flip either half. The spectator can decide. Well, since these are coupled piles, if we randomly flip either one, they're now, quote, mirrored piles. What does that mean? That means the card on top here is now related to the card on the bottom here, and vice versa. This card here is related to the bottom of that one there, and it's true as you go up and down each packet. So these are mirrored packets. Well, you already have seen what we can do with mirrored piles, right? We can do this really fun swapping procedure to get our pairings at the very end, right? Okay, so since we have 8 cards in each, the spectators allowed 7 swaps altogether. Okay, and they can allocate those however they like among these 2 piles. So maybe they'll want 4 swaps here. So 1, 2, 3, 4, and then you set that down like that. And then we have 3 swaps left. 1, 2, 3. Okay, very good. That's 7. And then you set aside this pair here. Okay, so this will be one of the special pairs at the end. Okay, so we have 6 swaps left. Maybe the spectator will ask for 2 of them here. 1, 2. That leaves 4 for over here. 1, 2, 3, 4. And then we set aside the new top cards. There we go. We have 5 swaps. Maybe we'll do 4 over here. 1, 2, 3, 4. And that leaves 1 swap to complete the set of 5 for over here. 1. Set aside that pair. And maybe we'll put it over here like that. Now we should have 4 swaps left. So maybe the spectator will ask for 2 on each. That's fine. So 1, 2, there you go. And 1, 2 for that one. Set aside the new pair right there. Okay, 3 swaps total left. 1, 2, we could put all of them here. 3. You can have all the swaps on just one pile if you like. Set aside that pair. Okay, and then we have 2 swaps left. How should we allocate those? Maybe 1 on each. 1, and then 1. Oh no, we have 2. We have 2 left. Yeah, that's right. Yeah, 1 on each. Okay, I said that right. Okay, set aside that pair. Very good. I can't count. And then now we're down to just 1 swap. Maybe they'll allocate it here. 1 swap. And now we'll set aside this pair right there. And then we're left with this final pair right here. Okay, very good. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 pairs. Now, do you remember what characteristic or what number we kind of stored in our short-term memory, a number, and that number is going to allow us to kind of divine what happens at the very end here. So if you remember, for this first routine, it was the number 4. We talked about thinking of the 4 seasons of the year as a way to remember it. Or there's 4 suits in a deck of cards, however you want to remember that. But what did the 4 relate to? Well, the 4 related to how many pairs we had that consisted of the same card value. Do you remember that? And so what you can do here, now the spectator doesn't know that you know that, right? Or that you remember that. So you can go here and kind of pretend that you're getting some type of message or feedback from the cards and go, well, I wonder how many of these cards match in color, or how many of them match in value, like 2 aces or something. Oh wow, wait a second. I'm getting a really clear picture as to how many of these actually match in value. That's interesting. Let's see, let me focus on that for a minute. Yes, I can see it in my mind's eye. 4 of these pairs consist of cards of the same value. Okay? Now, they may be of different colors, that's okay, but the same value. Let's check to see if I'm right. Are 4 of these pairs of the same value? Oh, those aren't of the same value. That's a fail there. Let's see, we need 4 of them, is what I'm claiming. Oh, that's a fail there. We're not doing very well. Oh, we found one. Check that out. In fact, they're 4s. That's interesting. So we found one pair that consists of cards of the same value. Oh, we found a second one. Yes. Okay, we only divined 4 of these altogether. We have 2. Let's see, what are these? Nope, that's a no match in value. Let's see, how about these 2? Oh, we got a couple of queens. Yes. So that's a 3rd pair. Oh, we only want one more matching pair of values. See? Okay, what about this one here? Oh, yes, 2 7s. Okay, so what we do not want to happen is we do not want these to match in value. Otherwise, it's blown. Okay, so are these of different values? Well, if I got a correct signal from the cards, they should be of different values. And they are. Yes! So we got matching pair and values. 1, 2, 3, 4. And the others don't. How in the world were we able to do that working together, considering all of the random choices that you made when it came to mixing and randomizing these cards? I think that is just amazing, okay? And it is actually, but it is true that it's just mathematics too. So it's not real magic.